This is Level 2, Video 6, which we are covering Chapter 2, Section 4, Reasoning in Algebra. This is the final video lesson for Level 2. The first thing we're going to take a look at and take notes on are a bunch of properties that we have seen and heard of from algebra that we'll be using to justify work in geometry. And we're going to start linking all the conditional statements that we've been working on and how they associate to geometry problems, or better yet, how we justify the solving that we've done in algebra that we're going to apply to geometry. So these properties start off with the most basic, which is the addition property. We've been taught that if you add the same things to both sides of an equation, then it will remain true. The equal sign will remain true. So for example, if I was to say if A is equal to B plus 4, notice this is an if-then statement, then we can all say that A plus 8 is equal to B plus 12. What we have to recognize is, even though this is not a traditional step in algebra, it's definitely true. If A equals B plus 4, well, if I add 8 to A, I have to add 8 to the other side. B plus 4 plus 8 would equal B plus 12. Sometimes the addition property is very obvious, where we add the same thing to both sides in order to eliminate a number. Sometimes it's a little more subtle, where we say, oh, we added 8 to both sides. This allows us to see the next three properties. We have a subtraction property. As long as we subtract the same thing from a true equal equation, then the result will also be true. Again, if A is equal to B plus 8, this is our true hypothesis, then A minus 2, so I subtract 2 from the left side, will equal B plus 6, because I subtract 2 from the right side. 8 minus 2 becomes 6. Now, traditionally we might do something like subtract 8 from both sides, in which we might have A minus 8 equals B. The multiplication property says that if A is equal to B, then if we multiply A times 5, it will be the same thing as multiplying B times 5. And finally, the division property says that if A is equal to B, then A divided by C will equal B divided by C. As long as one little thing, C does not equal 0, because we don't know how to divide by 0. It's an undefined value. Okay, substitution property is our next one. As we move beyond addition, subtraction, and those, we come into this term substitution that we used quite a lot in algebra. Substitution tells us we have to have two conditions. If A equals B and C is equal to A plus 10. So these two things have to be true. Not one condition, two. We have A equals B and C equals A plus 10. My conclusion is I can now say that C also equals B plus 10, because I have substituted the value of A with the value of B. They are equal values, so wherever I see A, I can replace it with B. Now, if B was the number 30, then I could replace C equals 30 plus 10. A and B just represent numbers that we can replace for each other. Now, the final property of equality that's going to show up here is the distributive property. The distributive property teaches us that A times the quantity B plus C is equivalent to A times the B plus A times the C. We have distributed the multiplication of A across addition. Now, these are the properties of equalities because they're used when we have actual numbers, values, like the lengths of segments. There are a few properties we will use when we discuss congruence. These will be the properties that happen to occur for equality and congruence. My first example will seem a little odd because it's so obvious, yet when we get into the geometric proofs that we want to study, it's going to become critical. The reflexive property. Like a reflection, when you look in the mirror, you see yourself. You see the exact same thing. Things do not change. The reflection property tells us that segment AB is congruent to segment AB. Something is always congruent to itself. Angle A is congruent to angle A. This conclusion can be made based on the reflection property in important situations where we might be looking at shapes that share a part. And we want to show that those shapes are exactly the same by discussing how they have the same part. So AB in shape number 1 is the same thing as AB in shape number 2 because anything is congruent to itself. Finally, we have the transitive property. Now, this can be of equality or of congruence. And we have two examples here. If segment AB, and now these should have segment symbols on them, we'll even attempt this right now. Segment symbol, segment symbol, segment symbol. If segment AB is congruent to segment CD, and segment CD is congruent to segment EF, so we have two conditions here, then we can jump from AB congruent to EF, because we have a middleman. This actually looks a lot like the law of syllogism, in which you have two if-then statements. If A, then B, and if B, then C, you can jump to A, then C. And that's similar to what's going on here. If A is congruent, AB is congruent to CD, and CD is congruent to EF, because they are both congruent to CD, we know that AB is congruent to EF. Same goes for angles. If A is congruent to B, and B is congruent to C, then A is congruent to C. So now what we're going to do is look at some examples of how we blend geometry and algebra and these reasons. First, we'll look at this example here. We have segment DT, which is 60 units long. Segment DS is 2x minus 8, and segment ST is 3x minus 12. We've seen examples like this before, and we've even done problems like this on the first level test. Find the value of x, and then find DS and ST. Now, I've been encouraging you guys to write down the geometry formula. And in this case, we would write ds plus st equals dt. Now, the addition for today is that on our work now on, we must write y. Why is ds plus st equals dt? Because that is the application of the segment addition postulate, which says part plus part equals whole. Now, the next thing we're going to do is take ds and write 2x minus 8. We're going to take st and we're going to write 3x minus 12. We're going to take dt and write 60. This is called substitution. Remember that if I said if a equals b, we can replace them. So if ds equals 2x minus 8, I can replace wherever I see ds with 2x minus 8. That is substitution. Now, from here, we're just going to do our basic algebra. We're going to take 2x and add 3x. And we're going to take negative 8 and add negative 12. And we're going to call that combined like terms. That was not on the previous page, but it is something we want to write down now. Combining like terms is a justification for our step. It's almost like if-then statements. If this, then this because of substitution. If these equals 60, then this equals 60 because we combined like terms. If 5x minus 20 equals 60, then 5x is equal to 80 because I added 20 to both sides. That's the addition property. Now 5x equals 80. If 5x equals 80, then x equals 16 because I divided by 5 on both sides. This is the division property. If, then, because. If, then, because. Now finally, we found x equals 16 and we wanted to find ds and st. So ds was 2x minus 8 and I put in 16. My justification here for both of these would be the substitution property. Okay, let's go to one more example. Now we have an angle up on the board and we have given that the measure of angle AOC is 39 degrees. Here's our angle with points A, O, B. We have AOC and little angle BOC. We're going to start off with, just like the previous slide, saying that the measure of angle AOB plus the measure of angle BOC equals the measure of the big angle AOC. And we have to write down why. How do we know that's true? On the previous slide it was segment addition postulate. We're talking about angles now. Angle addition postulate. Now, if this is true, then we can say that 2x plus 10 plus x equals 139. This is substitution. If 2x plus 10 plus x equals 139, then 3x plus 10 equals 139. What did we do here? If, then, because, we combine like terms. If 3x plus 10 equals 139, then 3x equals 129. Why? Because we subtracted 10 from both sides. If, then, because. If 3x equals 129, then x equals 43. Why? Because we divided by 3 on both sides. The division property. If, then, because. So there are two examples of how we use the algebra properties and looking at a geometry problem to justify our work. This should be good for us to get through assignment 6.
Good job, Dad. But can we please have one more example?
One more example?
Yeah.
Alright, one more example. This one is a little bit different, so maybe Preston is right. Maybe we need another example. Here it says OB bisects angle AOC. And all I'm given is AOB and BOC. I'm not given the big angle this time. Part plus part just isn't going to work. But I read what's on the board here and I think to myself, if OB bisects angle AOC, then the measure of angle AOB must be equal to the measure of angle BOC. Why? What's our justification here? It's not substitution. This is an angle addition postulate. What could this be? Well, it definitely comes from the word bisect. And we know that if an angle is bisected, it divides into 2 equal parts. So we justify this with the definition of an angle bisector tells us that this is true. Now from here, this becomes the same as the previous examples. If AOB equals measure of angle BOC, then 4x equals 2x plus 40, substitution. If 4x equals 2x plus 40, then 2x equals 40. Check to make sure you understand that this is the subtraction property. I subtracted 2x from both sides. Now if 2x is equal to 40, x is equal to 20, I divided by 2 on both sides, and that is the division property. A majority of the work on assignment 6 will be you making a decision that between the if and the then, what property was used in order to justify the then. Remember that if 2x plus 40 was the if, and the then was x plus 20, you're asking yourself, how did you get from here to here with the division property? How did we get from here to here with substitution property? That's it. That concludes video number 6 for level 2, and that is it for all of level 2.